I'm very happy to be here presenting robots as social goods, empowering users to direct interactions. And so because this is an AI seminar, I want to just start with the question of why robots? So why do I care about robots? Why should you care about robots? And robots are, in general, a way of interacting with the physical world. So they can be an assistive tool for different tasks. So in this case, we have a robot assisting people with spinal cord injuries or limited mobility to help them feed. We have different fetching tasks. So you can imagine you have a robot in your home and you say, hey, fetch me my laundry or fetch me my milk for the morning. And the robot will go sort of autonomously get your laundry. And there's various other assistive tasks that you might imagine, for example, like cooking or crafting or fixing various things. And then robots can also be a collaborative tool. So here's an example of a robot assembly task where a robot's sort of handing people parts of this structure and they're kind of collaborating to build the structure more quickly. What? So this paper specifically, I believe, was during COVID-19. Well, COVID still exists, but yeah. Another example could be collaborative lifting. I don't have a cool video, but here's me and a robot collaboratively lifting this tray. But we could also think of maybe collaboratively lifting a heavy box, for example, upstairs. And many more like creative tasks, which we'll see some examples throughout the talk today. So here we have this general purpose robots wording. What do I mean by general purpose robots? What I mean is robots that can be used for many different tasks as decided by users. So people who are using the robot or sort of end users, as opposed to people who designed the robot. So we can think of morphologies, for example, robot arms or mobile manipulators, where really they can do somewhat of an arbitrary range of tasks, or at least many different tasks. Whereas things like autonomous vehicles or Roombas, robot designers or robot manufacturers design them for a specific purpose. And it's pretty hard for end users to adapt them to different tasks. So that's kind of what we're going to be talking about today. Thinking about general purpose robots. Oh, and I should mention, feel free to interrupt at any point for questions, but I'll also have some specific pauses we'll ask. So where are general purpose robots headed? I think a lot of industry and academia centers around this vision of the home robot, and specifically this sort of like robot butler idea where you have a robot, you own it, so sort of one family owns one or more robots, and they can help you do anything around the house, like chores or different tasks. And then industry, especially recently, is very into humanoid robots as sort of the morphology that can accomplish this goal. And this model of you're a family and you own a robot, or you're an individual and you own a robot in your home is really great for a lot of reasons. One, you can sort of personalize it over time, right? You own this robot, the robot's in your house, so you have lots of time to interact with it. You can customize it to yourself. If you want to paint the robot a certain color, go ahead. And right, you can use it whenever you want on a whim. So you might wake up at 3 in the morning, say, I need a robot to do something, and it's right there. But I want to think a little bit about alternatives and whether this model of robot ownership or sort of the future of robots is equitable to everyone. So let's start with a bit of a motivating example. I love motivating examples. So here we have Alex, who will be a recurring character in this talk. And unlike in this sort of family home sort of scenario, Alex has roommates. So this is a twist. One of these roommates may or may not be the Lorax. It's pretty hard to know. But right, Alex and her roommates might not want a general purpose robot in their apartment. Either it's too expensive or one of them feels uncomfortable, especially if we think of humanoid morphologies. They might not want a robot sort of walking around the apartment all the time. But that doesn't mean that Alex's access to this potentially transformative and very helpful technology should be restricted. So we can think of a task where maybe Alex has some unassembled bookshelf she needs help assembling. Her roommates are out of town. And instead of her owning a robot, maybe she can go to her local library. She can borrow a robot for the afternoon. The robot helps her assemble. Maybe the robot helps paint it. And then she can return the robot to the library for the next person. And so this sort of example is, getting back to the title of the talk, is an example of robots as social goods, or sort of robots for everyone. It's thinking about how to expand the access to general purpose robots so that more people can use them. And of course, in this example, right, these interactions, we don't have this long-term personalization benefit. It might just be for an afternoon, but we need these interactions to be successful, both from the user side and as well as to complete the actual task. So in that case, it was to assemble the bookshelf. Yes.
So I think you might need to repeat the question. Can I think of this as analogous to like a tool library where you go like, oh, I need a drill, and you go get a drill, right?
Absolutely. That's a good analogy. There are things called libraries of things, even where you can go and like borrow a sewing machine. And I think that's a very good example. And getting into future work will draw even more analogies between the two. But yeah. Okay, so some preliminaries to talk about how to make robots as social goods and make that interaction work. Let's think about what capabilities robots will have in the future. So this is somewhat of a forward-thinking talk. But robots will almost definitely have some form of teleoperation. And what teleoperation means is the person is sort of directly controlling the robot. So here we have a physical twin of a robot. The person is moving this sort of copy of the robot, and the arm itself is copying that motion. Of course, the robot will have some autonomy. So they could be a set of autonomous policies where a policy dictates the task and the behavior of the robot. It might be trained through different means, but it'll know how to do a bunch of basic things autonomously. So we expect a robot to be able to autonomously pick this water bottle up. And of course, because even as people, we can't know everything, the robot will have some form of learning mechanism. So some way of adapting to or learning after deployment. So it needs to learn because it will try and pour the onions in, and it'll miss the bowl a little bit. Okay. So how do robots learn? Well, in this talk, we're going to sort of use reinforcement learning as our paradigm that we think about for getting a policy or learning policy. So here are several older reinforcement learning videos, but quick intro to reinforcement learning, though I know this audience is probably very familiar. We have a Markov decision process where basically the agent, or in this case robot, is observing the environment, taking actions which affect the environment, and then receiving some reward as defined by a designer. And over time, the robot learns to maximize the reward it receives and can perform a task. And this paradigm is very flexible, and you can learn a very wide range of tasks from this paradigm. Okay, so then given the capabilities, given how robots learn, how can we make robots work for everyone as social goods in the scenario? So one option is to make them as general as possible. So we can learn to do as many tasks in advance as we can. This is a very common approach in the robot learning community. We can think of making them as adaptable as possible. So a robot's in a new environment, it needs to be able to very quickly adapt to its environment and learn to do new tasks. That's sort of its own set of approaches that we need to think about. Note these are all additive. And then because we can't expect to know everything the robot might face, we could also think about empowering users to be able to direct and sort of dictate the interaction themselves. So right, the first two is think about how can we as researchers enable the robot to be as capable as possible. And this is thinking about how do we give users tools to sort of decide what the robot can and can't do specifically. Right, we can't predict everything, and even if we could, we might not want to because people like to have control over the technology. So we're going to call these empowerment strategies, which will be the focus of the talk today. And really, each of these strategies or methodologies are about sort of bridging the gap of control over the system from end users to designers. And so maybe this x-axis here could be different things like user expertise or the amount of time a person has to put into a system. And of course, these bubbles in reality, there's lots of overlap, and they're bigger, but this is just a visualization. And we're going to go 3 different empowerment strategies in this talk. So the first 2 are basically thinking about how users might interact with a reinforcement learning agent to sort of control it and direct the interaction. And the last one is thinking about what sort of information people might need about a robot to be able to do these things. Okay. Let's get into the first empowerment strategy, personalized task execution. We're going to go into the most detail of this one, and this is based on a paper that was published at HRI 2024. So the goal is to enable people to personalize robots' behavior in real time, whether that's for personalization purposes or to sort of express themselves through a robot. And specifically, we want to empower people with control over the behavior of a task it can already perform. So the robot knows how to do a task. We want to think about customizing, for example, the style in which and the way it completes the task. And we'll see some examples. So right, we've already seen these videos. RL is great at learning these optimal policies or this optimal way of completing certain tasks. And if we have a person in the loop, a person can teach preferences over these policies. So for example, in this case, it's the angle at which the robot should approach this table. But ultimately, with both of these approaches, we sort of end up with this single policy that needs to be retrained or retaught if a person's preferences change. So if my preferences change, I either need to change the reward function or I need to teach the robot my preferences. And there are scenarios where we might want to just be able to directly manipulate the robot's behavior. So we need a formulation of how to do this and give people real-time control over these robots. So we're going to call this formulation online behavior modification, sort of the framework or paradigm of what we want. And we're going to say there's 3 requirements of doing this. So 1, the robot must autonomously make task progress. So what this means is if I have my robot and I try and personalize it to myself, if it starts failing at the task, that's not great, right? So we don't want the robot to fail. Then we're going to say we want to define a set of behavior features that we can customize. So for example, the video earlier, there was this angle of approach to the table. We might also think about customizing the robot's speed. And these sort of different aspects of the robot's behavior, we're going to call these behavior features. And then we're also going to require an accessible user interface. So we have these behavior features, we're going to call these K for each different behavior features. And we're going to give people direct control over these features. And again, it needs to be interpretable and accessible. So if I change the speed of the robot, it shouldn't sort of oscillate in some unexpected way, for example. So to sort of solve this or go about doing this, we introduce this algorithm adjustable control of RL dynamics or accord, which is inspired by some previous approaches like diversity is all you need, quality diversity, or goal conditioned reinforcement learning. And let's step through this. Okay, so step 1 of this algorithm to do online behavior modification is we're going to define our tasks. So this is the Markov decision process. We have our state. And in this case, we're going to assume a vectorized sort of interpretable state that we can talk more about alternatives later. And then step 2, we're going to define our behavior oversight parameters, which are these behavioral features, by mapping them to the parts of the state that we care about. So for example, one position in the state vector might represent the robot's speed, and we're going to say, okay, that's a part of the state that we care about. Okay. Then what we're going to do is for each of these pairs, right, we have this K variable, which we're going to say is a variable with values between 0 and 1. And we have our state variables. We're going to define a mapping between them. And the way we're going to do that is by training discriminator networks, which are neural networks, which what they do is they learn a mapping from these K variables, again, from 0 to 1, to a certain part of the state space. So again, for speed, here we have kilometers per hour, 20 kilometers per hour. I'm excited about that. And you'll notice sort of in this example, we have a monotonic relationship. The algorithm itself will both sort of enforce this, and this gets back at interpretability. So as we increase K, we want to increase speed. So we train these networks to learn this mapping. And then because we also want to still complete the task, we're going to add in some task progress heuristic. So what these networks are doing is they're creating an unsupervised reward in the reinforcement learning sense that encourage the robots to learn the mappings from the state to these behavioral features. So if I set K to 0.5, there's a reward for the robot going at sort of a medium speed. But we also need a reward that says, okay, in this example where we have a walking robot, don't fall down because falling down is bad. So we have this sort of dual objective, and then we can train a policy that's adjustable. So we can vary the Ks directly. We can directly manipulate those variables, which then sets a goal for the robot. And as the robot reaches that goal, it'll also complete the task. Okay, any questions about the setup?
Over goals. Go faster, don't fall down. But maybe it's okay to fall down one time 10 if you go twice as fast. Can you repeat the question for the?
Yeah, so just repeating the question, and I think it's a great question and potentially a limitation of this work, which is what about incompatible goals? So we could imagine, I'm going to slightly simplify the example. We have S1, we're going to tie to like forward velocity, and S2, we're going to tie to like backwards velocity, and these are like very incompatible. So if we raise one, we might affect the other. In this sort of case, for this work, we're going to assume that these are all compatible within the can complete the task within this constraint of it still completes the task. So in the case of two Ks are sort of fighting each other, what the algorithm will actually learn is just to do the task and sort of ignore that reward for the most part. So it's sort of black box in that sense, and that is a limitation of this work.
Okay, Bell 110. Could you go 10 times faster? Can you think sure?
Oh, could you do that? Yeah. So to do that and to sort of get it. So again, the question is for people on Zoom, could we have a trade-off between these oversight parameters where one says, let's say, okay, let's go really fast and we can accept falling maybe 1 in 10 times. I think you could do that. To do that, you'd have to define additional parts of the state space that allow us to represent that. So in the state space, for these discriminated networks to learn, we might have to include when was our last fall, for example, and our speed. So that you could do, you just have to slightly manipulate the state space beyond what might be represented in the task. Awesome, thank you. Yes, Anthony. That is, where is action? So this unsupervised reward component doesn't have actions. You're correct, right? So because the state is all that's needed to generate this unsupervised reward with these discriminated networks, action isn't involved. We could include action if we wanted to define a specific behavior that's dependent on action potentially. So maybe we want some sort of oscillation where we need the last action the robot took. But action may be in our sort of task progress heuristic. Our reward is a function and it's a piecewise function. So what it ends up being is this unsupervised reward, the way we define it, and I can happily go into the math later in the talk or at the end, it'll always be a positive reward signal, and this heuristic will basically always be a negative reward signal. So it's a piecewise function, and yeah. Yes. The environment does come with our own reward. So step one was to define the MDP. We can define that. That is correct. And I think in a lot of the examples, we more or less treated the environment. We assumed the environment reward was also a negative dense reward with certain failure cases. So that's an assumption I didn't touch on in this talk. But for example, in this walking environment, a fall, right, is like a very large negative reward, but moving backwards is like a smaller reward. So it is, we do assume sort of three components. Okay, great. So what we need to do is study this in context as user interaction, right? And in general, having control over robot policies is applicable for a bunch of different tasks. So we could imagine assistive dressing, or maybe we care a lot about the force that the robot applies on us. Or hair combing is a popular task in HRI where people might have real-time preference changes. But like I alluded to earlier, we're going to focus on creative tasks. So what we did is we defined a painting task where the goal, and the reason we defined this task is because we wanted both a objective task metric as well as to encourage people in our study, which was an in-lab study, to want to express themselves and have specific preferences. So what the robot learned to do was trace over these different red shapes. So these were printed on pieces of paper, and we trained a reinforcement learning algorithm to basically trace over these different shapes with paint, and of course, like not hit into the table and get the robot dirty. And what we were looking for in this study was various qualitative outcomes from a user experience point of view. So could people in online behavior modification for this task feel like they could express themselves, feel like they could express their preferences, how much control did they feel like they had over the robot as the robot autonomously painted, and we'll see what that looks like. And for our quantitative sort of objective task metrics, we had coverage, which is how much of the red was still exposed after the painting. And users were told, you want to cover the paint or cover the red. And consistency, which we'll get back to, but that's basically how much the shape painted matched what was on the paper. And there's some interesting results there. So what? Oh, okay. So the question was, did the user have these metrics in mind explicitly? All we told the user was the goal is to trace the shape as much as possible, so cover the red as much as possible, while also sort of expressing our own individual style. And we left that sort of open for interpretation, but we also had some practice runs before we painted these two shapes. Okay, so this is what a chord looked like. So we gave people a slider interface, and we defined two behavior oversight parameters. One was this pressure of the brush, so we can make thin or thick lines. The other was the angle of the brush, so we could sort of rotate the brush as the robot autonomously painted. So the robot is autonomously moving along this path while these Ks are being adjusted, and then the algorithm learns to match those specific values. And again, people had practice with this interface on other shapes. So this sort of real-time control while the robot's also autonomously painting. So another thing we looked at was reinforcement learning. So we could imagine we have 6 predefined styles. A user selects a predefined style, and then the robot just paints it by itself. So there's no real-time user interaction, but this is analogous to a lot of existing sort of robotic applications where you say, okay, what's your preference? You pick it, and then the robot does the task. And then lastly, we wanted to look at what if we gave people a lot of control over the system, and this was our shared autonomy condition. So what this is doing is people have teleoperation control over the robot, so they can directly manipulate its actions, but while they do so, the robot's also trying to infer what style they want. So there were 6 discrete styles that we saw earlier, and as they're directly changing the robot's behavior, an algorithm is also trying to say, okay, I think you mean this style. And there's sort of a blending going on there. Okay, so we had people come in. I think we had 24 participants. We recruited them from around Boston. We had a pretty wide range of people, which was nice. And let's look at some results. Like, what did we learn from having people come in and do these paintings under these different conditions? So qualitatively, a chord in general, compared to the shared autonomy setting and reinforcement learning, people really liked it. So people both preferred it the most, and it gave them a very high sense of expressivity and control. So it was even surprising that people felt even slightly more in control over a chord than shared autonomy, because shared autonomy people had direct control over the robot. Some people commented it was because having direct control felt like too much control in a sense, so it was sort of hard to manipulate. But so that was great. That's sort of what we hypothesized. And we also saw some very interesting emergent behaviors. So this is when users or end users will do something that designers don't expect. So getting back to this sort of robots as social good model, or this public library example, a ton of different people are going to be using robots. We can't anticipate every way they're going to be using it. So in the shared autonomy condition, people made polka dots. And the way they did this was they brought the brush up from the paper, and then the reinforcement learning algorithm brought it back down. And so they could kind of play with it. And even though they knew they weren't like supposed to be doing this, because they're trying to cover as much red as possible, it was really fun for people. And then in a chord, what people were able to do is sort of wiggle these oversight parameters, which are essentially latent variables, back and forth very quickly. And it caused the robot to make very interesting brush strokes. So here we can sort of see very varied strokes in the painting. So quantitatively, getting back to this sort of objective task performance, the coverage, which was again how much of the red was covered, a chord in shared autonomy actually outperformed RL by a lot, which was very confusing for us at first, because reinforcement learning was trained to optimally do this task. So the reason for this is, we go back here, do people notice that all the shapes are like slightly offset from the red line? Well, the reason for that is as designers, the way we trained this algorithm was in simulation. And in simulation, we modeled the paintbrush as a rigid body. Okay. But paintbrushes have long bristles. And so the long bristles kind of drag behind the brush. And so even though the robot learned a quote unquote optimal policy in our setup, there was a limitation of us as designers that we didn't account for because modeling bristles is a very hard challenge. Yes.
At this point, like you train a simulation, then deploy it directly into the enterprise, the really main game.
Yes.
There you work functions that basically covering the red and
Correct. And also not to like hidden the table. Specifically, the brush that was used was filled with ink, and there was one time where it squeezed the brush too hard and ink exploded. So thankfully, that only happened once, but yeah. So what we did was we accounted for this. So the reason why accord and shared autonomy performed better than reinforcement learning is because users could compensate for this design error, right? We gave people control over the system, and they were able to make up for the flaw that we had initially had in the system. Okay, so if we look at, okay, what if we can just shift the painting and get rid of this offset? Then reinforcement learning has by far the best performance, which is this consistency metric followed by accord and shared autonomy, which makes sense because the more autonomy you have, in this case, the more you would expect it to do the task well. So kind of the key takeaway or the thing that we learned is that accord has this sort of comparable task performance to reinforcement learning without sacrificing this good user experience that giving people direct control through shared autonomy has. Yes. Yeah. Let me quickly. So the question for Zoom was, how did people use accord specifically to compensate for the offset? So the way they were able to do this, so it started off great, but basically the angle of the brush. So when they moved the angle of the brush, which was supposed to be fixed, in a combination, they could actually slightly adjust where the line was. Okay. So some limitations of this work, I think one of them was touched on with the question earlier, but we sort of were looking at relatively simple geometric features. We could imagine how could we define the robot's friendliness as a behavior feature or something more abstract. So there needs to be more work to make an algorithm that can efficiently learn that and define those things. And also we assumed that we knew what people would want to control in advance. So we had the pressure and the angle of brush, we predefined that, but we can't predict everything. So future work could look at having users come in and maybe co-design different features for different tasks. Okay, yes.
You showed three, one is fixed policy. The second was accord, third was shared autonomy.
Yes.
Did you have the full autonomy for the user?
We did not have full teleoperation for the user. And the reason is because that task specifically is potentially just too difficult within a constrained lab study for people to do effectively. And also, if we set up safety constraints, even with teleoperation, people might find a way to violate them. That's sort of a limitation on our part, but we didn't really view full teleoperation as kind of analogous. So the through line to all of these is that the robot's autonomously tracing the shape. And then it's just the style that we looked over the spectrum of control.
Was it learning in accord? So shared autonomy has no learning. The RL system when deployed is not learning. Because accord when deployed, learning.
Accord.
Reward, that's not here.
Yeah, so all of these systems, including Accord, we pre-trained in advance. So at deployment, there's no actual learning going on. So the learning part of Accord is the algorithm learning, one, the range over these different features. So for example, max and min angle, while it can also perform the task, as well as the sort of mapping that we can generate the sliders from. So we learn that in advance, and then we just give people the interface. So part of the motivation for Accord actually was we didn't want learning during the interaction because learning comes with sort of its own can of worms and its own effect on user behavior and potential burden if the user has to teach.
Cross the central gap, or the data for training for.
It crossed the central gap in this case. We needed to fine tune a little bit. So for example, I don't know if fine tune is the right term. What it learned in simulation for the range of pressure was actually too high in real. So the highest pressure, the brush exploded. So we had to sort of manually fix, okay, you can't go past this value. Thank you. Okay, great. So let's go to our next empowerment strategy, as we called it, which is facilitating innovative collaboration. And the goal here is to empower people to leverage existing behaviors of a robot to perform novel tasks. And again, we're going to focus on creative tasks, but I'll give some other examples. So the first accord was really about using an existing policy and customizing it. This is about using an existing policy for an entirely new task that's separate from the predefined. So motivating example, again, here we have Alex in her Oilers hat, which is exciting. And like we said, Alex has this robot. She may have gotten it from the library. It may be her own robot. And she's going to have some form of teleoperation, and the robot's going to have some set of autonomous policies. And one policy that she knows of and frequently uses is this carry liquid policy. So, hey, get me coffee. Hey, get me water. And of course, this policy brings cups from place to place without spilling the liquid. So Alex is a very creative person, and she decides, okay, I can leverage this to water my flowers. And the way I'm going to do it is I'm going to have it carry a cup of water over my flower bed, and then I'm going to teleoperate the wrist and sort of rotate it to water my flowers. So this is sort of a fun emergent interaction. And we're going to call this type of control partition control, where the robot's autonomously carrying something or has autonomous actions, and the user's partially teleoperating. So zooming out, we can think of more common examples. So cruise control in vehicles is an example of partition control, where the person's controlling the steering while the car is controlling the speed. Similar to drones, you can imagine a mobile manipulator. Maybe I'm controlling where it goes while it's carrying or doing a task with its arm. Okay, so what could go wrong with this example? And do we get this interaction for free? The answer is we don't get this interaction for free, especially if the policy was trained by reinforcement learning or some other machine learning mechanism. So one, what the user is doing is actually asking the robot to fail, right? The robot knows not to spill liquid because it's this carry liquid policy, and the user is saying, okay, spill liquid now. So how the designers designed the system to deal with that, the person might not know. So the robot might suddenly stop moving, which is a very common approach. And if the policy, so the user is interacting with the policy in a way that definitely didn't see during its training because it wasn't designed to do this task. And so sporadically out of distribution just means when it doesn't know what to do, it might behave sort of weirdly. So again, intuitively, as roboticists, the most common thing to do when we're out of distribution is to just stop and wait and be like, this is an unsafe thing, let's just stop moving. Another thing we might do is try and infer the user's intended task goal by saying, okay, what is the person trying to do with our system? But this is its own sort of area of research and very difficult. So getting back to shared autonomy, that's a lot of what shared autonomy is trying to do. So what was our sort of key insight to enable this interaction was that the robot should act in accordance with what the person sort of expects intuitively. So the person expects, okay, I've seen the robot carry this cup of liquid. Even during this interaction, the robot should behave similarly to how it has in the past. Does that make sense to people? Okay, great. So algorithmically, we introduced this algorithm, imaginary out of distribution actions, or IOTA, which is just a high level overview real quick. What we're going to do is in our current state, we're just going to ask, are we out of distribution? If we're not, so that's the bottom, that's fine. Just keep acting as you would otherwise. If we are, what we're going to do is imagine that we're in a state that's in distribution, or imagine that we're in the most similar state that the person has seen before. So we'll see what that looks like in an example. But basically, the intuition is we're going to actually pass in a fake state to the policy such that the behavior of the policy isn't as it would be out of distribution. And then we're going to continue with partition control. So we're going to combine the robot's autonomy and the user signal and sort of repeat this loop during partition control. So like Accord, we want to study this with end users and see if we can sort of have successful interactions. So we actually designed the flowering watering example. So that's why it was the motivating example. So we had a robot that carried cups of beads because water and robots and advisors don't mix. And we had a flower bed that had 5 flowers and could detect the weight of the beads. So we had people come in, they practiced teleoperating, they saw the robot execute the policy, which was, again, trained with reinforcement learning to carry these cups of liquid without spilling. And then we had them do this task with 3 different conditions. And what the task was specifically was trying to pour the beads out in each of these 5 flowers as evenly as possible. So this was just a metric that says an optimal pour is a uniform pour over these 5 flowers. How different was the user's pour? What? Oh yeah, the question is 0 water bad? Yes, this also penalizes underpouring, yes. Don't want dry flowers, and we also don't want overwatering. So this is what reinforcement learning looked like. This wasn't cherry-picked. So what's going on is, let's replay this. So the robot was trained to go across the flower bed, and the person has control of the wrist. And once the wrist moves, it's out of distribution. And in this case, the neural network just went backwards for some reason. Again, this wasn't explicitly designed or cherry-picked. This is just what happened. Interestingly enough, a couple very bright participants realized they could wait for it to get all the way over here, rotate the wrist, and then it would go backwards and pour out the beads. Okay, so as roboticists, let's think about this stop condition where we're out of distribution, let's just stop moving. And so people were able to do this task, but occasionally people were surprised. They were like, why did the robot stop? And they accidentally poured out almost all the beads in the first bin because they were like, it stopped moving, I didn't expect that. And so then what is IOTA doing? So what IOTA is doing is once it detects that it's out of distribution, it imagines that it's still on its like jolly path. Again, technically what it's doing is it's looking for a similar state in sort of its history of tasks. So it's not a perfectly straight line, but it's basically a smooth motion as the person pours. So result-wise, people expected IOTA to do this. They expected the robot to do what IOTA did, essentially. Of course, reinforcement learning was people were like, what's happening? They were very surprised by that. And this also led to the best task performance. So here, lower is better. This is IOTA, followed by stop, and then reinforcement learning. Again, very few people figured out how to use reinforcement learning to optimally do the task. And with stop, if people didn't pour out all the beads, they realized, okay, I'll rotate the wrist, go back upright, wait for it to move, and then pour again. And naturally, there's a strong correlation between meeting users' expectations and task performance. So I'm going to skip this future work slide, but any questions about that? Yes. So the question is, how do you measure if a state is out of distribution? That is a good question. What we did is we collected a bunch of rollouts of the robot carrying cups of liquid. So we had sort of a data set, and then we trained what's called like a deep out of distribution detector, which again, I'm happy to get into the math later, but all it's basically doing is saying, is this state similar to states I've seen before? Yes.
And the robot is imagining a state in its history, and then you're thinking that maybe that's not surprising to the user. But doesn't that depend on how the states and actions are encoded? So for example, if you're taking the action is left and the robot keeps moving left, then maybe the thing is expected. But if the action is apply this much voltage to this motor, and then the robot just keeps applying that much voltage to the motor, that may not be that may be surprising to the user because they're not thinking in terms of voltages and motors. I'm thinking like
Yeah. So the question for people on Zoom was, the meeting users' expectations sort of assumes that the state-action relationship is like interpretable to the person, one, and makes sense in the context of the system, two. Is that sort of correct? So yeah, I think that is a very good question. It is partially dependent on the system representation being able to capture the parts of the task that are aligned with what the user expects. So that is true. So in the pouring example, or in most geometric robot motion examples, there's a tight relationship between the state representation and the actions that affect the state. And then we have the user's control, and we can sort of look at how they change. But in the voltage case, that is potentially something where IOTA might even break the system. So that's a good point. Yes. That is also a good question. So the question on Zoom is, how do you map the out of distribution state to the closest state? For time, I didn't go over that, but basically we defined a distance metric that captures state similarity. And again, in the context of robotics, geometric distances work really well for a lot of state similarity representations, but in higher dimensional tasks, for example, autonomous driving or image-based tasks, what state similarity means and how that's aligned with the user's understanding of state similarity is, again, sort of an open research question and actually a popular area of research currently in HRI. But there's, yeah. Yeah, so in that case, it was just physicals. Okay, so I'm gonna sort of speed through this last work because I want to get to some future work. So this is all about informing people about a robot's performance, right? We had these different tasks and they were all sort of novel, right? Users were doing these unexpected things and we want to encourage that. But people need to know about what a robot can and can't do to do those things. So what does an informed user look like? So naturally, robots will definitely know how to like stack cups and stuff, but can people use a robot to brush their cat, for example? And to do that, they need to know about how safe is the robot, how likely it is to annoy the cat, and so on and so forth. Similarly, if a person knows about a robot's performance and they know that it might fail at a task, so if it's going to carry a vase and the robot says, okay, I'm not good at carrying vases, the person might be ready to swoop in and catch it. So the empowerment strategy here is just try and inform end users, potentially novices, importantly, about a robot's capabilities, such that they can use the robot for different tasks. So the way we went about doing this is we said, okay, well, how do experts and designers judge a robot's capabilities? They typically collect large data sets in different tasks and see how the robot performs based on what's called task success rate. So how many times the robot succeeded at a task versus how many times it failed. But in the case of users, right, they're just using a robot for this single task in this one-shot interaction. They're not collecting a bunch of rollouts and saying, how well did it perform? So the purpose of the study was to sort of look at the overlap of types of information that experts use and report in scientific robot learning evaluations, and what these novice end users, types of information that they need to use robots for different tasks. I know I'm kind of speeding through this, but this is real quick what a common robot learning evaluation looks like. It's typically a very controlled lab setting where you have a robot arm do some task like close the toaster, and then you report task success rate for a bunch of different algorithms that are dictating the robot's behavior. And we said, okay, can end users, so not robot designers, sort of, how do they interpret these evaluations? So what we did is we did an online study where we basically just showed these people and said, okay, what is your judgment of the robot? How well do you think it will perform on a task given prior task success rates? And we also did an in-person study. And quick takeaways was we actually found end users are pretty good at using things like task success rate, which is intuitive, to judge how a robot will perform, but they also want a lot more information than what's reported in robot learning research. So for example, people want to know about best case failures or worst case failures or most likely failures. They want to know how fast the robot can complete the task. And also people on a novel task, we actually found a pretty interesting result where some people, if you ask the robot, hey, do this task, and the robot says, I haven't done this before, but I think I can do it like 50% of the time. Some people really like that 50%. Some people say, I don't trust this robot. What have you done in the past that's similar? So we sort of saw some interesting information preferences. Okay, so in my final minute here, I just want to talk about some future work. So again, to have robots that work for a bunch of people, we introduced these empowerment strategies and justified it by saying we need these for robots as social goods because a bunch of different users will be using them and we can't predict how people are going to use these robots. So we should give them different amounts of control over a robotic system. So that stars future work. And I also am thinking about sort of socio-technical problems with robots as social goods. So not just from a technical algorithmic side or a study side, but also from a society impact point of view. So an empowerment strategy that I want to work on in the future is having control over feedback. So people teach robots in various different ways. For example, learning from demonstration or corrections, or saying, hey, robot, that was good or bad. And when we teach robots or teach AI agents, for example, ChatGPT, we have some expectation of how our feedback will affect the system. And this is actually fairly understudied. So typically we just think about how can we use feedback to optimize performance. But if I say, hey, robot, that was bad, that means different things for different people. So thinking about how to give people control over that interpretation. And then finally, getting back to the socio-technical impact point of view, we have a workshop submission at HRI this year, which is about robot lending libraries. Can we actually have libraries that can lend out robots? Libraries are just an example of robots for social goods, but what are challenges that come from the setup? So technically, I think we saw some technical challenges, but there's also things like privacy concerns of having a shared robot resource. There's how should the robot behave when it's in a certain community that has certain preferences over how a shared good should maybe behave. And the organizers here are listed. I want to shout out specifically Callie, who many of you might know. She is one of Matt's PhD students, who is great and helped us write the submission and proposal for this workshop. And yeah, thank you very much. Thanks. A lot of this work was done while I was at TUS. So thanks to my previous advisor, Elaine Short, my co-authors. And now I work with Serena Booth at Brown, who's amazing. So yeah, thank you to Serena, and all the publications that I talked about are listed here. Thank you.